So let's talk about percent yield and atom economy. What do we mean by these terms? I know we've defined them, I know we've used them a little bit in some of the terminology, some of the words, some of the worksheets we're using, but let's go ahead and kind of discuss what it actually means. What percent yield and atom economy both do is they both measure the success or efficiency of a reaction, but they're both coming at it from a different perspective. So first, let's discuss percent yield. Percent yield is a more commonly used way for us to talk about the success of a reaction. Percent yield is calculated by taking your actual or experimental yield and dividing this by your theoretical yield and taking this ratio and multiplying it by 100%. What do all these terms mean though? Well, your actual or experimental yield is the amount of product that you actually obtain from a reaction. How much did you actually get out of a reaction? Okay, so if you put two things together and you're trying to make a specific product, how much did you actually get out? That relates back to your limiting reactant. When you talked about limiting reactants, and we saw that if we know how much we start with each piece, we will limit how much we can actually make in the reaction. All of that's interrelated. We want to take that amount that we actually obtain of that product and divide that by our theoretical yield. Our theoretical yield is how much could we have made if nothing else went wrong, or nothing else happened, or we had 100% efficiency on the reaction. So the actual and experimental yield are the same thing. How much did you actually obtain, or how much did you prepare or produce in your experiment? Your theoretical yield is how much product could your limiting reactant actually produce. This is the most common way for us to represent the efficiency of a reaction. You're going to do this in Gen Chem 1. You'll see it come back in Gen Chem 2, especially in lab. And if you take organic chemistry, you're going to calculate percent yield a lot. In literature, when people do new reactions, they represent the efficiency or success of the reaction by calculating percent yield. The other concept we want to discuss is atom economy. So the difference here, percent yield, we have to use stoichiometric ratios to get there. So in order to find our theoretical yield, we have to use a stoichiometric ratio or stoichiometric calculation here. And this is based on that limiting reactant. For atom economy doesn't really concern itself with how much did I get out. Instead, atom economy concerns itself with how much do I put in to do this reaction in the first place versus what is the molar mass or molecular weight of my desired or target product. So atom economy is a more recently developed concept. It's actually one of the 12 principles of green chemistry. So this umbrella of green chemistry has been around for a while, but the first book was developed in about 1998 or so concerning green chemistry. And there's 12 main principles of this concept. All 12 principles, the focus is to kind of go towards a more sustainable or more environmentally friendly type of chemistry, being more proactive in our thinking about what's going into our reactions to make what we desire. And can we find more synthetic routes that are more environmentally friendly or more sustainable or less harmful or less wasteful? Atom economy deals with that waste side of things. It looks at what is the molecular weight of your desired or target product divided by the molecular weight of all reactants that went into the reaction. And again, multiplying this by 100%. We often multiply these by 100% because people just do a lot better with percentages. If we leave these in fractional form or even decimal form, it's hard for a lot of people to understand what that really means. But percent, we can quickly understand. If something's 50%, we've got half, we're good. If something's 80%, it's even better. If something's 100%, even better. We see that very quickly. If we tell someone it's got a ratio of 0.9, that just doesn't really compute the same way as saying 90%. So always make sure you're multiplying by 100% to put these in percent form. So quick example here, let's think about M&Ms. Let's say we do a reaction and we put in enough supplies to make 100 M&Ms. That means our theoretical yield would be 100. But at the end of the reaction, we count up all the M&Ms that we have, and we find that we only made 80 M&Ms. 80 divided by 100 times 100% gives me 80%. An 80% theoretical yield, or 80% yield, is actually a very good yield. And we'll talk about on the next slide about when what can cause a yield to be lower. But you should never actually get 100% yield on a reaction or something went wrong. We'll discuss that as well. Let's look at atom economy though. Let's say that we put in everything and our molecular weight of all reactants, let's say we put in 100 M&Ms. But we only want the green ones. We're only interested in the green M&Ms. Out of 100 M&Ms, we count up all of the green M&Ms. And by chance, we ended up with 37 green M&Ms. This gives me an atom economy of 37%, which is much lower. Our percent yield is great. We got 80% out. But our atom economy is only 37%. So it really depends on the reaction. Some reactions will have a very high percent yield and a high atom economy. Some will have a very high percent yield, a low atom economy. Some will be a low percent yield, but a high atom economy, and some will both be low. So these can work constructively or destructively together. And sometimes we care about atom economy, sometimes we don't. Sometimes we care more about percent yield, sometimes we don't. It really depends on the reaction and what the focus and goal of your reaction actually is. So I said that your percent yield is not going to be 100%. Students get really thrown by this because they think, well, it's close to 100, it's got to be good, right? Not always. There's things that can cause your reaction to not be 100%. Most often, you're going to see the reaction is actually under 100% yield. And what causes this? What causes the reaction to be lower than 100%? Well, first, your reactions don't always go to completion. We don't talk about this a lot in first semester. In Gen Chem 2 is when you're really going to discuss equilibrium. But you can think about every reaction as a spectrum. On this spectrum, some reactions are very product favored, meaning they're going to make all the product. Everything is going to react and make a product. Some reactions are very reactant favored. What I mean by that is when I mix two reactants together, nothing's going to happen. No reactions are going to occur. I consider this to be very reactant favored. They stay in reactant form. Then there's reactions that just kind of sit in the middle. And in the middle is a relative spacing. Where do we mean by the middle? But these are in equilibrium. Let's say you and your best friend move into houses next door to each other. You're living on campus for your junior year and you're now living in houses that just happen to be right next door to each other. Where are you guys going to hang out? Well, you'll probably hang out at your place sometimes, at your best friend's place sometimes, and sometimes you might just hang out right in the middle of your two houses if it's nice out. In Texas, it can get kind of hot, so that's probably not going to happen in the middle of summer, but fall and spring, maybe you're just going to hang out right in the middle of between your houses outside. You've created an equilibrium. You don't have any preference between one space or the other. You guys just like the middle. You like hanging out in the middle because you can hang out together and both be by your houses. It's kind of what a reaction is doing too. There's some reactions that just prefer to be in the middle. They've produced some product, but the reaction, we'll talk about this in second semester, but the reactions can actually go forward and backwards. And so much has been produced, now it reaches an equilibrium. We'll talk more about what that means in second semester, but equilibriums will cause a reaction to not be 100% because it stopped at some point before all of it produces a product. You could also have impure reactants. The chemicals we buy to actually do reactions are very rarely 100% pure. To get a 100% pure reactant is very expensive. It takes a lot of money because you have to purify the reactant. You may purify it yourself, but that also takes time and money. Most often we'll buy chemicals that are anywhere from 95 to 98% pure, and we'll use those. That little percentage of impurity there means that bit is not going to make the product we desire. So therefore, we cannot have 100% purity because we didn't even start with a 100% pure reactant. You can also have side reactions that can cause other products to form. These may form with your impurities or they may form with your actual reactants. You'll deal with this more in organic chemistry, but you'll find that some reactions have multiple pathways they can take, meaning they can produce different products. Some products are favored in certain conditions while others are favored under others. but sometimes it's just a competition on who can get there first. Some of the product may also be lost through things like filtration, being left in your reaction vessel, or just lost in the reaction itself. It doesn't get lost to the ether. It gets lost, either left behind somewhere, it gets washed out somewhere if you're doing a wash on something. There's lots of places that stuff can get kind of go missing. It's not really missing. We can tell you where it went, but it does not come out in the final product. All of these things will cause your reaction yield, your percent yield, your actual yield to be less than your theoretical yield. Some of them can also cause your percent yield to be greater than 100%. So if you have side reactions that cause a product to form that has a higher molar mass or higher molecular weight than your desired product, it's going to add more weight to your final product than what you were expecting. That higher mass is going to cause your percent yield to be a little higher than we were expecting, and it can cause it to be over 100%. More commonly, and more often than not, the reason you get a percent yield greater than 100 is because you have impurities, but most often it's because you have your solvent still present. In general chemistry, most often your solvent will be water. Water is what we call insidious. Water is very hard to dry off of your sample. Your sample may look completely dry. It may feel dry to you, but water is still going to be present. It takes a couple of days for the water to really dry off of a product. And all of that can cause your yield to be higher than 100%. So let's go ahead and work an example here. It's a very common reaction completed by Gen Chem students across the globe. Non-science, nurses, Gen Chem 1, Gen Chem 2. If you take Gen Chem 2 lab here at TCU, you will do this lab. It's an organic synthesis reaction, but it's a fun lab, and we can often do it in first semester or in a first year Gen Chem lab. So we're going to synthesize aspirin. The chemical name for aspirin is acetylsalicylic acid, and it can be prepared by heating salicylic acid, which has a chemical formula C7H6O3, with acetic anhydride, C4H6O3. So we're going to react C7H6O3 with C4H6O3, and we're going to produce salicylic acid and acetic acid, C2H4O2. It tells me that the formula of aspirin is C9H8O4. I apologize, my regular pen for my laptop stopped working. And so I want to know if I react 2 grams of salicylic acid. So 2 grams of this. And this is heated. For heat, we put a little triangle symbol over the arrow. Just means heat. With 4 grams of acetic anhydride. If the actual yield of aspirin is 2.10 grams, this is my acetic acid, so I don't care about this one. What is my percent yield, and what is my atom economy? In order to do this reaction, first I need to know the molar masses of each species. So you should always have a periodic table with you whenever you're doing chemistry problems. Carbon has a molar mass of 12.01 grams per mole. Hydrogen, 1.008 grams per mole. And oxygen, 16 grams per mole. Let's go ahead and add these up. For acetylsalicylic, let's add up salicylic acid first. Salicylic acid has 7 carbons, 6 hydrogens, and 3 oxygens. This has a molar mass of 138.12 grams per mole. For molar mass, I use this, what I call a script M. We use a capital M a lot in chemistry, so I use a script M to identify molar mass. Acetic anhydride has 4 carbons, 6 hydrogens, and 3 oxygens, and it has a molar mass of 102.09 grams per mole. And acetylsalicylic acid, or aspirin, has 9 carbons, 8 hydrogens, and 4 oxygens, and a molar mass of 180.2 grams per mole. Now, you may ask, why did I keep 2 decimals here, 2 here, and only 1 here? To answer that question, I'm going to tell you guys to go add up the sig figs. And you should see that with the numbers I used, I should have 1 decimal place for my salicylic acid based on sig figs. So, next thing I need to do, now that I have the molar mass of each species, I need to figure out what is my limiting reactant. Is this my limiting reactant, or is this my limiting reactant? In order to do that, I need to do the calculation to see which one's going to run out first. There's 2 different ways you can do this. You can compare them to each other and see, do I have enough to react all of this? And is the other species left over in excess? Or you can do it where you figure out how much product can you make from each species. I'm going to go ahead and figure out how much product I can make from each species, specifically because I know I'm trying to calculate percent yield, and I know how much product I have here. So I'm going to go ahead and do that so I can do one fell swoop on the calculation. So I'm going to use SA for salicylic acid, AA for acetic anhydride, and ASA for acetylsalicylic acid or aspirin. So the number of grams of acetylsalicylic acid if salicylic acid is the limiting reactant. I have 2 grams of salicylic acid. Convert that to moles. Remember, when in doubt, convert to moles. We're always going to convert to moles. We cannot compare masses to each other because the atoms themselves have a different number of protons, neutrons, and electrons. We can, however, compare molar mass. So this is grams of salicylic acid. So 1 mole of salicylic acid is equal to 138.12 grams of salicylic acid. Used our balanced equation to convert to moles of acetylsalicylic acid. This reaction is nice in the fact that everything is 1 to 1. So 1 mole of acetylsalicylic acid to 1 mole of salicylic acid. And then convert to grams of acetylsalicylic acid. I know that there's 180.2 grams of acetylsalicylic acid per 1 mole of acetylsalicylic acid. It's always a good idea to check and make sure that your units have canceled out. So grams of salicylic acid, moles of salicylic acid, moles of acetylsalicylic acid, and I've got grams of acetylsalicylic acid as my final unit, which is correct. So as long as my conversions are correct, I will get the right answer. Go ahead and do the math on this problem, making sure to multiply and divide where appropriate. And I come out with an answer of 2.61 grams of acetylsalicylic acid. Why did I keep 3 sig figs here? Because I have 3 sig figs here. I need 3 sig figs in my final answer. I had 5 here, and I had 4 here. Molar mass does limit your sig figs. Now let's see how many grams of acetylsalicylic acid could I make if acetic anhydride is my limiting reactant. I start with 4 grams of acetic anhydride, convert that to moles of acetic anhydride, it's 102.09 grams of acetic anhydride per 1 mole of acetic anhydride. Convert that to moles of acetylsalicylic acid. And convert that to grams of acetylsalicylic acid. Make sure that your units have canceled out. So grams of acetylsalicylic acid, moles of acetylsalicylic acid, or moles of acetic acid, I apologize, and moles of acetylsalicylic acid, giving me grams of acetylsalicylic acid. Then go ahead and multiply and divide as appropriate throughout the equation. And I calculate out 7.00 grams of acetylsalicylic acid. So, looking at these two numbers, which one is smaller? Clearly this one is smaller. That means that salicylic acid is my limiting reactant, and I can produce up to 2.61 grams of acetylsalicylic acid or aspirin. So for my percent yield, I'm going to take my actual yield, which is 2.10 grams. I'm going to divide it by my theoretical yield, which is 2.61 grams. And I'm going to multiply this by 100%. And I see that my final answer here is 80.5%. Again, I have 3 sig figs here because I have 3 sig figs in my original values. The percent symbol, this does not limit sig figs. This has 3 sig figs and this has 3 sig figs, so my final answer needs to have 3 sig figs. So percent yield, 80.5%. Now let's look at our atom economy. Give ourselves a little bit of room. Atom economy, again, is looking at the molecular weight of your desired product or target product divided by the molecular weight of your starting reactants. So 180.2 grams per mole divided by the sum of 138.12 grams per mole plus 102.09 grams per mole times 100%. So go ahead and plug in your calculator. 180.2 divided by the sum of 138.12 plus 102.09 times 100%. My final answer here, 75.02%. And note the differences here in my sig figs. My answer here, I have 3 sig figs. Because I have 2.10 and 2.61. That limited to 3. But in my atom economy, I have 4 sig figs. Because I'm just looking at what came from my molar masses or molecular weights of each species.